development was the recognition, which really was led by Stefan again, that this becomes an equality in the diagonal limit for interacting theories. So by diagonal limit, I mean that you take this deformation to be very narrow. Roughly speaking, its width should be smaller than the characteristic wavelength of the excitations in your state, and diagonal. And then in that limit, this becomes an equality. So you really have a very direct relation between energy and entropy. Okay. And again, this was first proven holographically using when you run the Mani-Taglianaki proposal built on RT. And there is another proof in the works, and has been for like more than a year, by several of my students, Levine, Shabazz-Moghadam, and Chandrasekaran, together with Faulkner, and I think one of his collaborators. There is a proof which I think will come out soon for general interacting theories, not just also for gravity tool, that this becomes an equality in this diagonal limit. For interacting theories only, not for free theories. So there's a discontinuity there. There's some operators that come down in the free case that spoil this equality. Great, so all that happened, but the thing that I really want to highlight is that I think it's a very big deal that you can do this, that you can learn something about quantum field theory in this way. And moreover, I think we should not be fooled by the fact that we can prove this within relativistic quantum field theory. As physicists, that doesn't mean anything to us, because relativistic quantum field theory has not actually been tested in the regime that is accessed by a statement like this. This is a very low energy regime. It's highly quantum coherent. It's relativistic because the deformations are along null directions. So the relativistic part is built into the statement. This is very different from what we probe here at CERN, for example. So this is a part of relativistic quantum field theory that has not been experimentally tested. And this is a prediction of what will be found in such experiments. And I'm not aware of any fundamental obstruction to carrying out experiments that will test statements like this. This could be done in somebody's basement lab, maybe. You need a lot of control in the quantum state. You need to be able to control how much of it you get to access, and take differences and so on. But I don't know what the best setting is for probing this. But I don't, it's not going to take building a galaxy scale accelerator and then making a black hole. And that's important because this is a consequence of a guess about quantum gravity. That does not have to be true. We don't know if this is true. And so if that makes predictions that we can test at low energy, I think that's a big deal. That's not something that kind of connection we normally don't have. Okay, so how am I doing with time?
About 35 minutes.
So about 20 minutes. All right, so then I can get to some ongoing work. And I guess I'll just switch these now. Actually, you know what? I'll do this differently. Yeah, no, this is not moving. I'm actually going to leave this one up and erase the other one because, okay, God, how did I do this? Come on. No, I want to stop. Yeah. All right. Oh, too much. This is really annoying. Like, what would have been wrong with just doing this by hand? It's a tiny blackboard. Okay. Yes.
About the focusing theory, what you raised.
Yes.
How does it impact the rating difference?
This doesn't contradict that. So, for example, so the effective stress tensor on vacuum energy, when you contract it with a null vector, is zero because it's proportional to the metric. And so vacuum energy does not affect the expansion of light wave at all. Yeah. Thank you.
So then it doesn't hold?
Yeah. So there's no assumption here that the strong energy condition holds. That would be bad because it clearly doesn't hold. Okay, so my next iteration of this scheme here is going to look like this. Okay, and I'll try to explain what these cryptic things mean. This is Engelhard wall, and Engelhard is here, so anything that is confusing about this, ask Netta. And this is quantum Engelhard wall, which we will try to formulate. So this is based on ongoing work that I'm doing with Len and Arvin, both here. So let me start by explaining the classical Engelhard wall construction, which I think is a beautiful field. And I will explain very quickly, and I'll leave out a lot of details because I understand that Netta's going to explain it much better in her talk. But let's just consider a black hole. For the purposes of what we're discussing here, this doesn't really have to be a black hole in asymptotically anti-de Sitter space, but it's going to be a black hole formed from the collapse of some pure state stuff. Okay, so this is fundamentally in a pure state. If we do have a gravity dual like in ADS, the CFT will be in a pure state. And there's an age-old question of how it makes sense Beckett-Sense formula for the entropy of a black hole if we know the entropy is actually zero. And of course the way that we would like to make sense of it is the same way that it makes sense of me handing you a box filled with hot gas or something. And maybe the hot gas is in a pure state, but if I don't tell you which pure state it is, then you're going to have to coarse grain, and all you know is the temperature and the volume and the pressure or something, and from that you can compute the level of your ignorance. In other words, the entropy. That is a coarse grain entropy. By now feeding the information about which exact quantum state this gas is in, then the entropy is of course zero. We'd like to have a similar story for a black hole. And I really want to stress this is a very old and very deep problem, which I think these guys completely solve. I don't think that this is getting nearly enough attention. So their statement is, well, first of all, you can't actually always do this, and there are good reasons to believe that, for example, if you just pick some surface on the event horizon, there is no good coarse graining prescription. marginally trapped. So here I'm talking purely about classical statements. It's classically marginally trapped. In other words, the expansion of the light rays here is 0, and the expansion of these light rays here is negative. Say that L is less than 0. Okay. And these surfaces have special properties that allow them to carry out their construction. For a black hole that isn't seeing much accretion anymore, those surfaces will be very close to the event horizon. Okay, but in general, they could be quite a bit inside. Okay, and there's some restrictions on these surfaces which I will not go into in this talk, and that I'm sure Neda will discuss, but that's sort of the key assumption.
Picture is there a picture that's not shown?
Yeah, in this picture there's a weak amount of, I'm assuming, roughly speaking, a genericity condition, that there's not exactly zero energy going in.
If you get zero energy going in and just Hawking radiation, then you're
We don't have Hawking radiation, this is right now the classical. We're in the classical part.
Yeah.
So here's the construction for the coarse graining. What you're supposed to do is forget something, right? We have to forget something to get coarse graining, and we have to keep something. Like in the case of the box, it was the volume and the pressures, right? So what they're telling us to forget is the inside of the surface. So here's article 0. Everything on this side we forget. Everything on this side called the outer wedge we keep. So this, we can make that one Cauchy slice of the outer wedge, and that gives us really information about all of this. This stuff we keep. This part of the geometry we forget completely, and now we try to put as much entropy as we can on this side. Okay. Now, this is a sort of hybrid argument where we have to know a little bit about quantum gravity to understand what it means to put as much entropy as possible on this side. But I want to stress that ultimately the construction itself is purely classical. Okay. So what Neda and Aaron noted, what it means to put a lot of entropy on this side, is it means, thanks to the Ryu-Takayanagi proposal, we know what that should mean. It means that you should try to put an external surface of as much area as possible on this side. So you invent a new auxiliary geometry which has an HRT surface, an external surface. Sorry, I never actually defined this. Most of you have to know this, but it's a surface in which both non-expanded vanish. Okay, so this is locally stationary under any variation, stationary in the area under variations in any direction. It isn't really extremal, by the way, it's stationary, but everybody says extremal surface. So you try to put on it. Why is that the right thing to do? Because we secretly know that at least in ADS-CFT, the way that the entropy of a quantum state would be computed is exactly by the area of the extremal surface. That is homologous to the boundary. Here we're keeping the whole boundary, so we're looking for an extremal surface that is, maybe a sphere, topologically a sphere, somewhere inside. Inside the space-time, something I can't contract further. I didn't have that in my original. So there was no extremal surface. But I can build a new space-time. And now there's two things that you can do. First of all, you can show that, let's call this surface here, again, sigma. And there's some hypothetical extremal surface, x, somewhere in your auxiliary geometry. And you can show that the area of x is less than the area of sigma using the null energy condition. And a bunch of other insights. This is relatively easy to show. Okay. So you already know that the most you can possibly hope to do is to find an extremal surface that has area equal to the marginally trapped surface you started from. And then in a very construction, Neda and Aaron showed exactly how to get that. And the way that they get that is they define their new geometry in terms of initial conditions specified on a null slice. That's basically an extension of this K congruence of the old geometry, backward in time and inward, in which you require that this is basically completely stationary. You take the geometry of your marginally trapped surface. By the way, it doesn't have to look like some kind of curved horizon or anything like that. It could be quite wildly shaped. And you're allowed to just sort of transport that as a fixed cross-sectional geometry along a bunch of light rays. Of course, there's hard work involved. You have to show that that corresponds to consistent initial conditions. It satisfies constraint equations and so on. But you basically arrange for the expansion to be 0 and for the shear to be 0 along here, and to have exactly the same intrinsic geometry. And then, you started with a situation where the L expansion going this way was negative, the K expansion was 0. You're waiting to find some place where the L expansion also becomes 0. You've already arranged for K expansion to stay 0, but then you want to find a place where the L expansion is 0, and you have to prove that that exists. And so there's some differential equations, and you have to know their properties, and you can prove that you'll eventually find such a place. Okay. So again, the details I'm sure is something to hear from Neda about. And so then this shows that you can always achieve this at no greater area for your extremal surface. And so now there's a quantum state that's dual to this new geometry that you've constructed, which has entropy given by the area of your original marginally trapped surface, which is a good measure of the area of the black hole. Anyway, if you don't like that one, you're out of luck. That's the one that can be coarse-grained. So that's the story. Again, I want to stress that while the motivation for this choice comes from ADS-CFT, you wouldn't maybe have thought of the role of stationary or extremal surfaces as being so fundamental without having ADS-CFT. The construction itself is a purely classical construction, and what I now want to discuss is what happens when we try to elevate this to a quantum construction. And by this I mean that, again, we consider an expansion in GH bar where there's some non-trivial quantum matter. We're interested now not just in coarse graining. We're not just interested in what coarse graining corresponds to the Bekenstein area equals entropy term. We're interested in what coarse graining corresponds to the generalized entropy that I have. In other words, the area of sigma plus the entropy outside of sigma. Okay. What is the thing that I need to do to find a quantum state on the boundary here which really has that much entropy, area plus S out? Okay, which in some sense satisfies the same criteria. You're holding the exterior fixed and you're varying only the interior. Okay, so that's sort of a task. Okay, and so here are some key things that we noted will have to be accomplished, or conjecture will have to be accomplished. Again, this step always involves a conjecture in order to carry out this construction.
Yeah. So how different is this new geometry from the internal black hole?
geometry, so I stress that the intrinsic geometry of this surface does not have to look like Kerr at all. And then we're not changing that ever. So this is like a bifurcation surface, but it doesn't look like the bifurcation surface of any of the black holes we know. I found it quite surprising that you're allowed to do this, but that's sort of the non-trivial content of this construction. Yeah. But it has to be two-sided. Yeah, sorry, I should clarify. Yeah, thank you. So in that sense, it's similar. That if you could keep going, and this would be some sort of black hole, white hole situation with another boundary on the other side, if you like. In fact, what they like to do is have a sort of CPT reflection to define the other side in terms of that.
But there's supposed to be a CFT state that's dual to this geometry.
There must be a CFT. I mean, but it's going to be a mixed state if you look at both sides. Yeah, exactly.
That's a different not the thermal state.
Yeah, exactly. Exactly. Yeah. That's right.
You must have said this, but did they assume the Einstein equation with an energy condition as restricted?
So you have to use the null energy condition, for example, for this result, that this is true.
So the usual classical null energy.
Yes. So the game here is going to be exactly the same story as before. The classical statement depends on the null energy condition. You're going to want some quantum statement that no longer relies on that. Right. So let me maybe just draw this again because it's gotten a little messy. I better speed up. So here's my black hole. Now we consider a quantum marginal surface, so we need big theta k to be equal to 0, and big theta L is going to be negative. If we didn't do that, the classically marginally trapped surfaces are actually outside of the horizon and it would be a disaster. So it's immediately clear that this would not work. So we want to start with quantum marginally trapped surfaces. Again, the quantum expansion, the k direction is then exactly 0 here. But we would like to carry out the construction in the same manner as Engelhard involved otherwise. In other words, we'd like there to be a stationary null surface so that we can control both the L and the entropy until we get to a quantum extremal surface, X, somewhere down here. And what that means is that what we're really demanding is, so remember the quantum expansion being 0 means that theta plus the derivative of the entropy on the outside, as I vary along here, is 0, but it does not mean that each of these things is separately 0. And this is a very important step here. This is kind of the only thing I want you to really pay attention to in this construction demo. Can illustrate now. So right here on the initial quantum trapped surface, we do not have the property that these two things are separately 0. And we want that property as we follow down here. Okay. We want theta equals 0 and as out prime equals 0 separately. Okay. And in order to do this, we know for this part that Engelhard and Wall had to demand. That includes in particular that the stress tensor, the flux of energy across the surface vanishes, and that the KL component of the stress tensor is everywhere equal to whatever it was on the initial sigma. Okay. That comes from demanding that theta is 0 everywhere. But then we also have this new property, we need S out prime to be equal to 0 everywhere on this part. In other words, we want S out to kind of stay the same. Whatever it was here, that should be the same as out once I look at the quantum state that I have on this slice. It's very unusual behavior for the von Neumann entropy. Normally, for example, all the entropy will increase if I give myself access to a bigger region, and all the measures of entropy will vary in interesting ways. But this is what we're going to do to make this happen. And so let's turn this around and take this to be a conjecture that a quantum state with these properties actually exists. Okay. All right. So this is now the conjecture. This is the analog of the, quantum area theorem that generalized second law is a guess. It's the analog of the quantum focusing conjecture, which was a guess. This is also a guess. Okay. But now let's see what that guess implies when we reduce this to a situation where we can make a quantum field theory statement. That's a situation where we really have a Killing horizon here, and we're very close to it. In other words, we're working perturbatively around a horizon on which all the light rays have infinite parameter length in both directions. Okay. And in that state, in that limit, what this tells us is that we have a state. Well, sorry, I forgot one important thing. I apologize. I forgot one important thing. One important conclusion that this property of the state has to vanish everywhere along here, little theta. But we also have the problem that little theta isn't actually 0 on my initial surface for the reason that I described. Only big theta has to be 0. And so I need little theta to jump a little bit by this amount from whatever value it has here to 0. And the way I can achieve such a jump in little theta is I have to have a spike in energy. I have to have a little shock wave sitting right here, which has to have either negative or positive energy, but localized as a delta function to take little theta from whatever is here to 0 down there. Okay, so this shock wave is going to strength. S h bar over 2 pi times delta of v minus v naught, if we consider this value here to be v and this point here is v naught, for v less or equal to v naught. In other words, I don't know what the stress tensor looks like here, that could be anything, but here I want it to be 0 except for a shock wave right at the cut. And that shock wave has to have a very particular strength. And so that's one of the predictions for the state that the conjecture exists. Okay. Now if we assume that this is true, we get something very interesting in the field theory limit. Maybe we get a state that proves Wall's and conjecture. Well, an ant conjecture is the following statement. So let this be a light ray. Let me just formulate it for gravity in 1 + 1 dimensions. And there's an ant that walks from right to left, let's say. Here's V0, and it's walked all the way to here, so it knows the quantum state rho right. And it also knows that globally, the energy is bounded from below by 0. And so it wonders, given what I know about rho right, what is the least amount of energy that I could still encounter as I get access to the other semi-infinite region of space that it hasn't seen yet? Right. And what Aaron conjectured is that this is the total energy is the energy that is already seen on the right, plus h bar over 2 pi times the derivative of the right von Neumann entropy evaluated at V0. So at any point V, I can compute the right von Neumann entropy, and I can look at the function of V and then evaluate it at V0. Now, how we came up with this, let's not go there. One way to say how we came up with this is that if this was true, then the quantum null energy condition follows. I think it's fairly easy to see that the derivative of this m is minus the stress tensor plus the second derivative of the entropy, and it's also fairly obvious that this derivative has a sign because we're looking at the smallest amount of energy that you might have, and if I place weaker restrictions on that by moving this point a little bit to the right, then that can only go down. Okay, and so it's pretty clear. I mean, it's not hard to see that this, if true, would imply the quantum null energy condition. But of course, it's a stronger statement. Okay, well, with state. It's so good. One thing that's fairly easy to show is this. You can't do better. That follows from general properties of strong subjectivity and monotonicity of entropy and stuff like that. Okay. So all you really need to do is find one state that achieves this minimum. And this state is exactly what does that. If this state exists, the state that we needed for the quantum Engelhard-Wall construction, then Wall's ant conjecture must hold. Okay. So again, we can say that we started with something that was purely a GR construction. We elevated it to a guess about quantum gravity, and we obtained a result in quantum field theory. And as usual, the result has been proven. And as usual by Faulkner. And unfortunately, he proved it before we wrote the paper, but his paper doesn't really check explicitly for these properties because that's not what he cared about. But there's a paper by Seyhan and Faulkner, and I'm probably mispronouncing this name, with a very beautiful algebraic quantum field theory construction that involves co-cycle flow and things I've never heard about in my life before, and which establishes all of these properties. So if you look at his paper, you can immediately check that all of these things are satisfied in the state that he constructs. So it is in fact once again true that if you believe that relativistic quantum field theory is valid, then yes, this is all true. Okay, but you could have discovered it more quickly this way. Okay, so unfortunately I don't have time to talk about my work with Maria Tomasevic, but if you guys want to talk about the Penrose inequality with us at any point, we would love to talk about that, and so I'll end with that. Thank you.
Any fairly quick question?
So you know how to make these conjectures because you know how to replace the area by the content area. So is there any other quantities that allows you to place in the game among the area?
I'm having a lot of fun with this game. My plan is to spend the rest of my career replacing the area with a generalized entropy in every formula that I find.
So what about others' area? Others' career?
Well, so well, let me actually give you an example. It's a little bit subtle. I mean, it doesn't always quite work the same way, and maybe I should just say one thing as a warning. Okay, so the Penrose inequality is a statement where, you say you have some trapped surface or marginally trapped surface of area A in the space-time, maybe multiple ones, but let's worry about a simple case, right? And then you would expect that means that there's a dimension horizon of bigger area outside of that, and by the area theorem that can't go down, so you're going to settle down into a black hole that has to have at least that area, and you ask what's the minimum mass such a black hole can have, well, it's a Schwarzschild black hole of that area, and by this you get an inequality of this form, which you can think of as a generalization of the positive energy theorem. Okay, so you'd expect the mass at infinity, like the ADM mass or Bondi mass, depending on exactly how you define things, to satisfy this. And now one thing that's very clear, I think first of all it's clear that this is again violated at the semi-classical level because you can put the negative energy out here. That in cases where this is initially saturated, like Schwarzschild, that can lower the mass on the outside and not change this area, for example, and violate this theorem. And so you want to have some quantum Penrose inequality, right? But this is clearly the wrong answer. Why is this the wrong answer? At least in asymptotically flat space, I think in some sense also in ADS, but let's talk about asymptotically flat space. It's clear that you can put as much entropy as you like at no cost in energy in soft particles at great distances. And so you can make this arbitrarily badly violated. So there's simply, there isn't by itself a relation between energy and entropy if you don't also constrain space somehow. And so this is clearly not the right answer. Okay, so our current guess is that instead of having classically marginally trapped surfaces that go here, we should think of quantum marginally trapped surfaces that go here but still use the area. It's not sure that this guess is correct, but I think there should be some generalization, and this seems to me currently the most plausible one. So that's the one we're exploring.
So, the zeroth law, the surface gravity of the stationary black hole is constant. It's related to the bifurcation surface, not the singular space-time. I'm just wondering in this proof by Engelhard and Wall, the presence of this sort of virtual bifurcation surface, you emphasized a couple of times that this marginally trapped surface need not be curl-like, so it could look like something with a non-uniform surface gravity. But again, on the other hand, it's not. And then they assume something like stationarity and projecting it to the